All right, so let's talk about our last application of thermochemistry, and that's actually calculating delta H's or enthalpies of reactions using literature values. So we can measure enthalpy of reactions using laboratory techniques, but we can also calculate them um, using given literature values of delta H's. And I'll show you how we do that here. And we are taking advantage of what's called Hess's law. And the notion that delta H is a state function. So, reactions, when we calculate enthalpies, because it's a state function, we don't have to calculate it in one step. We can combine multiple reactions in multiple steps to get to the same answer. And so that's what I mean here. As long as the individual steps of a reaction add up to the overall equation that we're trying to calculate, we can calculate the delta H value using what's called Hess's law. So Hess's law is that the enthalpy change for a reaction that you calculate, so delta H of a reaction, is the sum of all of the delta H values for each step. So those steps can come from literature values that we are given. So these literature values, I can give them to you on an exam, or you can look them up on tables. So let's look at the strategy of using Hess's law and combining multiple steps to get to an overall chemical reaction. So the strategy here, we can use Hess's law to combine reactions to obtain an overall reaction. So to do that, typically you're given multiple steps, each with their own delta H value. And so as long as those reactions add up to the overall reaction that we're trying to obtain, then all we have to do is add up those delta H's of each individual step. So the important thing is when you're looking at all of the different steps, you need to check that the direction of the reaction is correct. So if you have the wrong reactant or product on a given side with a given reaction, you'll need to reverse the reaction. So if you reverse one of the steps, you have to do the same thing to the delta H value that's given. So if your reactants and products aren't on the correct side, so you have to swap it, uh, change the direction of the reaction, you also have to reverse the delta H of that step. And we talked about this where enthalpy is an extensive process, so it depends on the material and the amount that you're given. So if you reverse the reaction, you have to multiply the delta H for that step, you have to multiply it by -1. So you change the sign of delta H. Next, so once you have the reactants and products on the correct side, you need to check the quantities or the coefficients in your goal target overall reaction. So let's say you have to double the amount of substances in a given step. So if you double a step, you also have to double the delta H value because, again, delta H is an extensive property. So if you double the reaction, you double the heat produced or consumed in that reaction. So whatever factor you multiply that step by, you must do the same thing to the delta H value. So yeah, so if you double a reaction step, then you also double the delta H value. Triple that step, you have to triple or multiply by 3 the delta H value. All right, so these are the strategies to use when applying Hess's law to calculate a delta H value for a given reaction when you're given multiple steps. All right, so let's actually use this strategy for an example problem. So this is like how a question on an exam would show up. What is the delta H value for this particular reaction? Where we have calcium hydroxide combining with SO3 gas to give calcium sulfate and water. All right, and so there's no delta H value here, but that's what we want to calculate. We want to calculate the delta H for this particular reaction. So we are given these different steps, these specific thermochemical equations. These are our steps that we're given to try to reproduce what is given. So the first thing we want to do with this Hess's law strategy is check that the products and reactants are on the correct sides. So I kind of do this stepwise. I look here, okay, in our target reaction, I want calcium hydroxide solid on the reactant side. So let's look at what's given. So in this first reaction, I have calcium hydroxide. It's right here. So how this thermochemical equation is written, calcium hydroxide solid is on the correct side. So we don't have to do anything to it. That's great. All right, so we don't have to do anything to that first step because calcium hydroxide is on the correct side. Next, let's look at the next component. So the other reactant is SO3. So let's look for SO3 in the given steps that we were given here. So I see the only place SO3 shows up is this second reaction. Let's ask ourselves, is it on the correct side? It looks like yes, it is. SO3 gas is on the reactant side. So that's great. So SO3 is on the correct side. So so it looks like these two steps are set up correctly where all the reactants are on the correct side. But now what about the products? There's a lot of other substances here. But what's great when we combine these thermochemical equations, we can cancel out some of the components. So like let's see here. We need calcium sulfate on the product side, so that's there. That's great. And we need water in the gaseous form, and water in the gaseous form is in this first step. It's on the correct side. But we see that there's an extra component here, calcium oxide solid. So if we look at our target chemical reaction, calcium oxide is not in our target reaction. But let's take a look at these thermochemical equations because we said the sum of the steps, as long as it equals the chemical reaction, then that's the enthalpy of that specific target reaction. So calcium oxide is here in the first step. It's a product, but we also see calcium oxide solid is a reactant in the second equation. So if we literally just add these two reactions up and combine everything, we see that calcium oxide is a product in one and it's a reactant in another. So you can think, okay, calcium oxide is produced in one reaction but consumed in the other reaction. So it actually cancels out because they are on opposite sides of the different steps. So it's consumed, it's produced and then consumed. So there's a net zero calcium oxide. So that's great because then when we add up all of the other components that don't cancel out, we get the exact chemical equation that is our target that we're trying to calculate. So I see, you have calcium hydroxide solid as a reactant, SO3 as a reactant. So I put both of those as our reactants in our overall chemical equation. And then we also have H2O gas and calcium sulfate solid. So you see here with these two chemical equations as given, these two steps, they add up to our target chemical overall equation. So since we added up each of these steps to calculate the addition of both of those steps, the combination of both of those steps, we have to also add up the delta H values. So the delta H, or the enthalpy of this overall reaction, is equal to the sum of all of those two reactions given. So the delta H is equal to positive 109 kilojoules plus negative 401 kilojoules. And so the delta H of this overall reaction, we didn't really have to do anything to it. We didn't have to reverse anything or flip it because I wanted a pretty easy, example for our first one. We just have to add them together. So our answer here is negative 292 kilojoules. So this example just kind of exemplifies that we can add up steps to get to a target chemical reaction and calculate its delta H of that overall reaction given certain steps. All right, so that example was pretty straightforward. So let's look at this other example. Okay, so let's calculate the enthalpy for this reaction. This reaction is ethylene gas plus water gives us ethanol. Calculate the delta H of this reaction given these two thermochemical equations. These are the steps we have to work with. So again, same strategy. I'm going to make sure that our products and reactants are on the right sides for the different steps. So I'm going to look to see where ethylene shows up. So C2H4, it's a reactant. So I'm just going to label these steps. I'm going to call this step 1 and this step 2, just so we can track of those. So ethylene C2H4 shows up in step 2, and it shows up on the right side. So I'm just going to leave that as is because it's on the right side. It's It has the right coefficient in front of it, so I don't need to do anything to that step right now. So let's move on to water. So H2O liquid, let's see where that shows up in these steps. So I see that there's actually two places water shows up. So water shows up in both of these steps, both on the reactant side. So I'm just going to skip that for now and focus on the other components first, and just hope that things cancel out and water is in the right place. So let's just skip water for now. Next, the product, so ethanol, C2H5OH. Let's see where that shows up in the given steps that we have. So I see that ethanol shows up in step one, but it's on the reactant side. So it's in the wrong place. I want to put C2H5OH on the product side because that's where it is in our target chemical reaction. So now we actually have to do some Hess's law stuff. So I want to flip where ethanol is. So I'm just going to kind of remind myself I want to flip this reaction. And so if we flip it, we have to do the same thing to the delta H value. We have to flip it. So I'm going to actually rewrite this equation so it's flipped. So down here, I will write, so I'm going to flip reaction 1 times -1. I'm going to flip it. So if I flip it, I will put the CO2s on this side. So 2 CO2 gas plus 3 H2O liquid. And I put the reactants, now it's on the product side. So C2H5OH liquid plus 3 oxygens. So I flip the chemical reaction, but that also means I have to flip the delta H value. So if we flip the reaction, we just multiply the delta H value by -1. So now it becomes positive. So the new delta H of this flipped reaction is positive 1,367 kilojoules per mole. All right, there we go. So because I flipped reaction 1, now I have ethylene and ethanol on the correct side, which is great. So let's just take inventory of everything and see if we can add up to the chemical equation that is our target. So ethylene, or sorry, acetylene, yeah, ethylene is on the right side, C2H4, and ethanol is on the right side. What about all this other stuff? So I see that there's oxygens. So I'm adding up these two reactions. These two. So the flipped version of step 1 and step 2 just as written. So you see here I have 3 oxygens on the reactant side of step 2, but there's no oxygens in our target chemical reaction. But thankfully, oxygen also appears on the product side of our flipped step 1. So those two components actually cancel out because there's 3 of them. There's 3 oxygens. They're on opposite sides, and so when we add them up, they will cancel. What else can we cancel? So if we look at the next component, there's 2 CO2s. CO2, carbon dioxide, does not appear in our overall chemical reaction. Again, thankfully, 2 CO2s are on opposite sides of those 2 reactions that we're adding up. So great. All those parts that we don't want, they cancel out perfectly. Lastly, the last component here is water. Remember how I said that we skipped it and just like hoped that it would cancel out? Well, it does cancel out. So we need 1 water on the reactant side. So I see in step 2 we have 2 waters on the product side, and in the flipped version of step 1 we have 3 waters. So 2 waters on the product side are produced, 3 waters are consumed on the reactant side. So how this cancels, those 2 waters will cancel, and all but 1 water molecule will remain on the reactant side in step 1, the flipped version of step 1. So now we've canceled everything that we needed to. So when we add up step 2 in the reversed version of step 1, you'll see that we get exactly the chemical reaction that we wanted to get at the very end. So let's see the overall reaction. It's now C2H4 gas. Oxygen and CO2 cancel. We were left with 1 water. So that's it for the reactants. Now if we add up the products, CO2, water cancels, and the only thing that's left is C2H5OH liquid. So you see that how we added up those 2 steps, how we arranged it, gives us the exact target chemical reaction that we want. So that's great. So now we need to make sure that we add up those delta H's how we calculated them. So in step 2, we didn't have to do anything to the delta H. Step 1, we already flipped it. So all we have to do is add up this step and this step that we flipped to get the delta H of the overall reaction that we calculated, or that we, pieced together through our puzzle. So delta H of this reaction is equal to negative 1,411 kilojoules per mole plus positive 1,367 kilojoules per mole. And so the overall delta H of this reaction is equal to, I have it here, negative 44 kilojoules per mole. Okay. So that is using Hess's law. In this example, we actually did have to flip one of the steps in order to get the product on the right side. All right. I like Hess's law. It's like a little puzzle. um, uh, working with the steps, flipping them, multiplying them to get your target chemical equation. But the big thing here is to remember that if you flip or multiply a whole chemical reaction, then you must do the same thing to that delta H value for that step before adding up everything at the very end to get your target chemical reaction. All right, so let's do one more example here. Yes. So let's do a little tougher one. This one has more components, but it's still exactly the same. This is our target chemical reaction, and we want to calculate the delta H for this with these two given steps. So again, it's the same strategy. Let's just make sure all the different components are on the correct side. So I'm going to just start with C2H2. So that's acetylene gas. So I will look at the steps given. So I'm just going to name them 1 and 2 so I can just keep track of them. So I see C2H2 shows up in the first step, the first thermochemical step given. The problem is that in the overall reaction, I want a 1 coefficient, but in step 1 that's given, there's 2 acetylenes. So that means that I have to divide all of the coefficients by 2. So I'm going to do that. So in step 1, I'm going to that over, multiply by 1/2 or divide everything by 2. And I'm going to rewrite it because I like to see all the coefficients and see how they cancel out. So if I divide by 2, step 1 by 2, I also have to do the same thing to the delta H value. So I just want to remind myself to do that. So to get the coefficient of 1 in front of acetylene C2H2, I divide everything by 2. So the new thermochemical equation for that step will be, 2 divided by 2. So 1 C2H2 gas. The coefficient of 5 divided by 2, so this is 5 halves O2 gas, gives us 4 CO2s, but I'm dividing it by 2, so 2 CO2s gas. And then lastly, 2 waters divided by 2, so 1 water, so H2O gas. And remember, we do the same thing to the delta H value. So delta H for this new reaction that I divided by 2 is equal to, I'm just going to do 2511 kilojoules over 2, just to remind myself that that's the new delta H value. Okay, so I have acetylene in the right place. That's great. So let's just move on to the next one, the next reactant. So there's 5 N2O gases. So the only place where N2O shows up in the steps that were given is right here. All right. But again, there's not enough of them. In the step that's given, there's only 1 N2O. And in the final chemical equation, there's 5. Also, it's in the wrong spot. N2O in step 2 is on the product side, but we need it on the reactant side. So we actually have to both flip this reaction and multiply by 5. So I'm just going to do that. So the whole reaction, I'm going to multiply by -1 to flip it, and to multiply by 5 so the coefficient matches. And then remember, you have to do the same thing to the delta H value. So times -1 times 5. All right, so let's rewrite that equation the right way. So I need to flip it and multiply by 5. So if I flip it, then N2O is on the reactant side, but also multiply by 5. So there's 5 N2Os there. All right, and now the reactants become products. So nitrogen gas, but 5 of them, So 5 N2 gases plus, so there's a half oxygen here. So a coefficient of a half times 5 is 5 halves oxygen gas. All right. And then our new delta H value for this chemical reaction, I'll just kind of remind myself 81.6 kilojoules per mole. So it's negative now because we flipped it, and it's times 5. So I'll just do it at the end when I add them up. All right. So I flipped it and multiplied by 5 that whole thermochemical equation. So now let's see, now that we've manipulated step 1 and 2, let's see if they add up to what we want. I really hope it does. So, um, we have N2O, 5 of them, that's on the correct side. So we have those. Acetylene, C2H2, that's on the right side. That's good. Um, the product, CO2, we have 2 CO2s there. That's great. We have a water, so that's there. It's in the right place, it's in the right quantity. And lastly, 5 nitrogen gases. And so we have that here in this chemical reaction because remember, our goal is just to add these up. So what's left over? Oxygen. So oxygen is not in the original chemical equation that we want, but thankfully it all worked out. There's 5 halves oxygen on the reactant side in step 1, and there's 5 halves oxygen in step 2. So they cancel out because they're on opposite sides. So oxygens cancel out, so that works out perfectly. So if you add these up, you get the exact chemical equation that was our goal, our target. So C2H2 gas plus 5 N2O gases gives us 5 nitrogen gases plus 2 CO2 gases and 1 H2O gas. All right, so there's our chemical equation. It all cancels out and we get exactly our target chemical equation we want. But that's not the answer. So, we solved the puzzle and made sure that it all fit, but we need to make sure we do the same thing when we add up the enthalpies of each step. So, to get the delta H of this reaction, we just have to take the sum of our manipulation of the delta H's that we took care of. So if you add up those two values, so negative 251 kilojoules over 2 plus negative 81.6 kilojoules times 5. So if you put that into your calculator, you should get the delta H of this reaction equals negative 1,664 joules. There we are. Yeah, Hess's law is kind of fun. It's like solving a puzzle. You just have to remember whatever you do to the chemical reaction, you must do to the delta H value for that step before adding up all of the step enthalpies to get your final delta H of that target reaction. All right, so let's talk about another application of Hess's law using literature values of enthalpy data. So this brings us to standard enthalpies of formation. So these values, these standard enthalpies of formation, are given in tables, and you're always given tables of standard enthalpies. So what is a standard enthalpy of formation? So we typically denote, so we know enthalpy means delta H, but what does of formation mean? So typically we denote standard enthalpy of formation as delta H, not with a subscript F to mean formation. So let's talk about what formation means. This represents the enthalpy or the energy required to form 1 mole of a certain compound from its elements in their standard state. So what standard state means is the physical state of that element at, what is this, at that is expected at 298 Kelvin and 1 ATM. So, most metals are solids. Many of the non-metals are, diatomic and gases. So we have to think about the standard states, how these elements exist in nature. All right. And so these delta H values are given in Appendix G of your textbook, and you're always given delta H of formations of compounds. And we can use these formation values to also calculate delta H of a given reaction using Hess's law. It's just a different application of Hess's law. So we need to think of, what does standard enthalpy of formation mean? It's the enthalpy or the energy required or heat required to make 1 mole of a compound from its elements in their standard state. So here's an example of the standard formation of ammonia gas, so NH3 gas. So the delta H of formation is given here. So this is what you would see in a textbook. The delta H of formation for ammonia gas is equal to this value. That to form ammonia gas is requires negative 46.19 kilojoules per mole, meaning that it requires negative 46 kilojoules to produce 1 mole of ammonia gas. But now remember, this is a reaction, so we have to be able to form what is a formation reaction. So that's what's given here. So we have to inspect the elements that make up the compound of the standard formation of the compound. So nitrogen, you have to think, okay, in its elemental form, what is nitrogen? Nitrogen exists in our world as N2 gas. So N2 gas will be a reactant because it's forming from its standard state elements. So N2 gas. But you note here that there's only one nitrogen in the chemical formula. But in nitrogen gas, there's two nitrogens. So we have to put a 1/2 coefficient to make sure that there's only one nitrogen. So it's balanced essentially. So there's one nitrogen uh, uh, combining with hydrogen to make your 1 mole coefficient of 1 ammonia. So we do the same thing to hydrogen. The next element in the compound is hydrogen, and there's 3 hydrogens. So we need to think, okay, what's the standard state of hydrogen in our world? Well, it's H2 gas. They're both nonmetals, so they're diatomics, diatomic molecules. So it's H2 gas. So we know H2 has to be one of the reactants. But again, we need to make sure the atoms themselves are balanced. So if we put a 3/2 coefficient in front of H2, that ensures that there's 3 hydrogens on our reactant side. And so you now see everything is balanced. One nitrogen combines with 3 hydrogens to give you nitrogen, or sorry, ammonia gas. And so also note here that standard state, I mean, nitrogen and hydrogen exist as diatomic molecules. They also exist as gases. So you have to make sure to include those gas physical states in your standard formation reaction. And so this is the reaction. 1/2 nitrogen gas plus 3/2 hydrogen gas gives NH3 gas, and the value for that delta H value is equal to negative 46 kilojoules per mole. And so, but typically in textbooks, you will only see this. You will see that the delta H of formation is NH3 gas. So in your mind, you have to be able to put together the standard formation reaction that's associated with this reaction enthalpy. And then I have some notes here. So fractional coefficients are okay here because we need to produce 1 mole of product. That's the definition of enthalpy of formation. It's the energy required to make 1 mole of that product. So use whatever stoichiometry necessary to make sure you're only making 1 mole of that compound. So let's actually practice writing out some standard enthalpies of formation. Or standard formation reaction. So the things to keep in mind if I ask you, okay, what's this standard formation reaction for CH4 gas? You have to remember this is what you're making. So all of these that I'm writing here, these are our products, all right? So this is our product. So I kind of have it started here. So CH4, that's our goal, that's our product. So now you need to think what are the elements of this compound in their standard state. And also note that I'm only making 1 mole of these products. And then if there's fractional coefficients at the end, that's okay. Keep them. You don't have to multiply by a multiplier to get rid of them. Just keep the fractions. It's all right. So this is our target compound. So let's just break it apart into the different atoms. So I see carbon here. Carbon in its standard state, it's like graphite, like or diamond. Carbon is a solid. So carbon solid, and it exists as just a coefficient of 1. So carbon solid. So that's our first element, and it's balanced because there's just one. Next, it's hydrogen is our element, and there's 4 hydrogens. So I remember, okay, hydrogen in its standard state is H2 gas. So H2 gas. But we need to make sure that those atoms are balanced. There's 4 hydrogens in CH4. I only have 2 here, so I'm going to put a 2 coefficient in front of H2 gas. Right? So this is the standard formation reaction for the formation of CH4. And so then if you look it up on a table in Appendix G, you can find the delta H of formation for this compound, and that represents this reaction occurring, forming 1 mole of CH4 gas from its elements in their standard state. All right, so let's keep going. So the next one, we're making a silicon hydrogen bromide containing compound. So again, you just look at the elements that are given. So silicon, silicon solid, plus silicon is under carbon. So remember our trends that they have similar states and they exist similarly. So just 1 atom there. Next we have hydrogen. Hydrogen exists as H2 gas in its standard state, but we need 3 hydrogens. So I'm going to put a 3 halves coefficient in front of hydrogen. So there's a total of 3 hydrogens on the reactant side. And then lastly, it's bromine gas, bromine. So bromine as in its standard state is a diatomic, so it's Br2 gas. Or sorry, it's not a gas, it's a liquid. So bromine is, it's like an exception to the halogens. It exists as a liquid in its standard state. And what's the coefficient? So we only want 1 bromine atom in our product, so I'm going to put a 1/2 in front of it. All right. So we're essentially like just building 1 mole of these products from their elements in their standard state with the correct coefficients to make 1 mole of that product. All right. Next, we're making sodium carbonate. So Na2CO3. What is it? Solid. So Na exists as sodium solid, but we need 2 of them. Plus carbon. There's only 1 carbon, so just carbon solid. Plus oxygen. Oxygen exists as O2 gas. We need 3 oxygen atoms, so I'm going to put a 3 halves in front of it. So that's it. Next one, nickel nitrate. So nickel nitrate, just nickel nitrate, yeah. So that is our product, nickel nitrate. And so note here that there is a parentheses. So total, there's 1 nickel atom, there's 2 nitrogen atoms, and there's 6 oxygen atoms. So keep that in mind when balancing your atoms. So nickel in its standard state is just nickel solid, it's a metal, right? And there's 1 of them, so that's good. So nitrogen exists as N2 gas, just like hydrogen. It's one of our diatomics. There's 2 nitrogens there because of the subscript in the parentheses. So there's 2 nitrogens on our reactant side, so we're good. Lastly, oxygen also exists as a diatomic, as in the gas form, and there's a total of 6 oxygens on our product side, so we need 3 O2s to become atom balanced, and so that's a solid, I forgot that. All right, and then lastly, NH4, or ammonium chloride solid. Again, remember, it's whatever is you're asking for, whatever the standard formation reaction is asking for, that is the product. So NH4, Cl solid, that's the product. So I just go through all the atoms. So the first one is nitrogen. Nitrogen in its standard state is N2. That's a gas, but I only want one atom, so I'm going to put a half in front of there. Next, it's hydrogen. H2 gas, that's its standard state. 4 hydrogen atoms, so I'm going to put a 2 coefficient. And lastly, chlorine exists as a diatomic, so it's Cl2 gas, but I only want 1 chlorine atom, so I'm going to put another 1/2 in front of it, so it's all balanced. So there are our standard formation reactions for these different compounds. So keep in mind when I ask for a compound or the standard formation of a compound, that has to be the product. And then for all of these reactions, they will have an associated delta H of formation value associated with them. And so you have to infer, because this is a formation reaction, that you are producing exactly 1 mole of the product or of the substance from its elements in their standard state. All right, so now that we've talked about delta H's of formation and how we can make those chemical reactions that are associated with the delta H of formation values given in the appendix, how does that relate to Hess's law? Well, we can use these delta H values to find the delta H of a a target delta H of a reaction in its standard state. So these delta H values that you can get in Appendix G, you can put them together to get the delta H value, delta H naught of a reaction of any chemical reaction. So, depending on the reactants and products given in a chemical reaction, if you take the sum of all of the delta H of formations of your products minus the sum of your delta H of formation of your reactants, so products minus reactants, you can calculate the delta H naught, meaning at standard conditions, of any reaction. So I want to note here that delta H's of formation typically exist for compounds. If there is an element already in its standard state within your chemical reaction, such as like oxygen gas, hydrogen gas, or something, the delta H for that element is zero. Because if you think about, if I asked you what is the delta H of formation for oxygen gas, well, you think, okay, there's oxygen atoms. Standard state of oxygen is oxygen gas, right? So this is what the reaction for the formation of oxygen gas would be. So you see that there's no change here. There's no change. So the delta H of this reaction is zero. So if an element appears in your target chemical reaction, then that delta H of formation value is already zero. So it kind of saves you a little bit of work. You only have to get the delta H of formations for more complex compounds. So are we going to do an example? Not quite. So this equation here, the delta H of reaction of a reaction given is the sum of the delta H of formations of your products plus the sum of the delta H's of your reactants, sum of products, sum of reactants. This is an application of Hess's law. So how does this work? It works just like Hess's law. So you're essentially taking the formation of products and subtracting your formation of reactants. So what you're essentially saying is like, okay, if we make all of the products from its standard state and subtract all of the reactants being made from their standard state, all the standard state things cancel, and you're only left with the compounds that we care about. So you might be thinking, do chemical reactions actually occur this way? They don't. So let's just call this delta H2. This is what we call that, and this is delta H1. All right, so we have our initial state. There's some energy requirement to make those elements into their standard state. And to get to your final state, we consume those elements to make our final state. So that's essentially what we're saying. But um, remember that delta H or enthalpy is a state function. So it only matters what our initial and final state are. The height or the elevation of change of the mountain is the only thing that matters, not the path that it takes to get there. So it doesn't matter that we go through the elements in their standard state to get to this total calculation, your delta H of your total reaction. It doesn't matter because delta H or enthalpy is a state function. But the thing is, so the way we calculate this and use Hess's law and delta H's of formation to get the enthalpy of a total reaction, these reactions don't actually occur this way. We don't actually make the elements and then consume the elements. All right, and I think that's what I have on this slide. Do reactions really happen this way? No, they don't. But because enthalpy is a state function, they don't have to. As long as the sum adds up to what we want, or the initial and final state are exactly what we want, then that energy difference is equal to the enthalpy that it is. So really, what's important here is that you know the steps to calculate the enthalpy of a reaction at standard conditions given delta H of formation of compounds. So let's actually put this to practice. So let's find the enthalpy of a reaction for the combustion of 2 moles of butane. So this is the total chemical equation where we want to calculate the delta H of this specific reaction, right? And so I already told you before that the delta H naught of a reaction, the naught there, equals the sum of the delta H values of formation of the products minus the sum of delta H values of formation of the reactants. All right. So we are given a bunch of, so this is our total reaction we're doing. We're given delta H values, and these come from Appendix G in these tables. So I have them all right here. and see that the states match exactly what is given. All right. So one thing I like to do is kind of just like write underneath the values what those delta H values are, and then I can put together my Hess's law equation to calculate it. So I see C4H10, that is negative 124.7 kilojoules. Is that what? Yeah, kilojoules per mole. Um, CO2 gas is negative 393.5 kilojoules per mole. And then water is in liquid form is negative 285.8 kilojoules per mole. All right, and so you see here, where is oxygen? Why didn't I give you oxygen gas, the delta H of formation there? But remember, oxygen gas is already in its standard state, already standard state. So there is no delta H of formation. Well, there is, but it's zero. It's already in standard state. So that means the delta H of formation for oxygen is equal to 0 kilojoules per mole. So that's easy. So for oxygen, it's 0. So now we can put together the equation that we will use to calculate the delta H in standard conditions for this reaction. So I'll just write exactly what values that I will put in. So again, it's products minus reactants. So first I will take the sum of all of the delta H's of formation of the products. So I'm going to just look at the products. I see that there's 8 CO2s. So that coefficient matters because it's the sum of all of the formations. So since there's 8 CO2 molecules, or 8 moles of CO2, we have to take into account 8 iterations of that delta H of formation value because it's in kilojoules per mole of CO2. But there isn't just 1 mole of CO2, there's actually 8 moles of CO2. So, how I will put this together, I'm going to do 8 times the delta H of formation of CO2. So, that one first. And then I will add 10, um, 10 of the delta H's of formation of water, H2O. All right, so that's the sum of the products. So you must take into account the coefficients. And then so it's always sum of products minus sum of reactants. So I put everything in parentheses just to remind myself, okay, add all of these up first. And then you want to add up all of the reactants too in its own set of parentheses. So sum of reactants. So let's look and see what that is. So the sum of the reactants is 2 because of the coefficient of 2 in front of butane. Is that what this is? Yeah, butane. 2 of the delta H's of formation of butane, so C10, plus 13 of the delta H's of oxygen. But remember, this is 0, so that's nice that it just kind of cancels out and you don't have to worry about it. Right? So that's how you set up the equation. So now let's actually put in the numbers to get exactly what we want. So sum of the products, it's 8 times, what's CO2? Negative 393.5 kilojoules per mole. So this is 8 moles, so those moles cancel. Whoops, I don't want to put a parenthesis yet. Plus 10 of the delta H's of water, which is negative 285.8 kilojoules per mole. I didn't give myself a. All right. And then, so that's the sum of the products minus the sum of the reactants. So 2 times delta H of formation for butane. So that's negative 124.7 kilojoules per mole. And then the contribution from oxygen is just 0. So we don't have to worry about oxygen because it's already in its standard state. So if we look at this, and add up all of those values, maybe I'll just do this. So it's 8 times negative 393.5 plus 10 times negative 285.8. So this part is negative 606,006 kilojoules minus 2 times negative 124.7 negative 2. Whoops. So it's in parentheses. So this is negative 249.4 kilojoules. All right. And so now if we finish the operation, so negative 6 2006 minus negative 249.4. That equals, let's see, negative 570 or 5,756.6 kilojoules. So that is the delta H of formation, or sorry, delta H standard state of this particular reaction. So this reaction in standard conditions will produce about almost 6,000 kilojoules worth of energy as written. Um, the negative sign says that it's exothermic, so energy is given off. All right. So the important thing to note here is that you will always be given these formation values, right? So writing them and associating them with all of the different products and reactants is important. And then when putting together your delta H naught of your reaction, you need to take into account the coefficients that are written in the reaction and the associated formation value that's given. And then you take the sum of the formation values of the products and you subtract the sum of the formation values for the reactants. All right, so let's do one more example where we use the same, so this is the last slide, we use the same Hess's law strategy here, but it's just a little different. So we can modify this approach to actually calculate an unknown delta H of formation value as long as we're given the delta H of reaction. So if we kind of go back here, in this particular question, we were given all the delta H values and we calculated delta H of reaction. But what if I gave you this value, delta H of reaction, and you calculated one of these values that was missing? So that's essentially what this question is saying. So let's calculate the delta H of formation for ethane given this information. And so I give you the delta H of formation of ethylene, so C2H4. So we know this value, and we are trying to figure out the delta H of formation for the product, C2H6. So you might be thinking, well, what about the delta H of formation of H2? Well, remember, H2 is already in its standard state, so the delta H of formation value is already 0. So if we put together the delta H of formation, or sorry, delta H in its standard state for this reaction, sum of products minus sum of reactants, so this is equal to, so sum of products minus sum of reactants. So if I just kind of put this together without any numbers, first off, our product is delta H of formation of our C2H6, and there's only one of them, so there's just a 1 coefficient in front of there, minus sum of the reactants. So delta H of formation of C2H4. All right, and I mean, we can also include, since it's the sum, also the delta H of formation of hydrogen, but we know that that is 0. So this is 0, so that's nice. So let's look and see what's given already in the question. So we have delta H naught of the reaction. So that value we know. We are trying to calculate this value, the delta H of formation of ethane, right? That's what the question's asking. And it also gives us from our appendix G, from the table, the delta H of formation of ethylene. So we have this value too. And then we know that this formation of hydrogen is already 0. So we have everything we need to calculate to solve for our product here. So let's just put those numbers in as written. So negative 137.0 kilojoules equals this number. This is what we're trying to calculate. 2H6 minus the reactant. So that's given as 52.3 kilojoules. And thankfully, all the coefficients are just 1, so we don't have to factor those in right now. So now all you do is plug and chug and solve for delta H of formation for C2H6, and you get this value, negative 84.7 kilojoules per mole. So that is the delta H value of formation of ethane. So we kind of just back calculated, we were just given different values, but we still use the same type of Hess's law reaction where we are getting or solving for the delta H of the reaction in standard conditions equals the sum of the delta H formation of the products minus the delta H of formation of the reactants. All right, and so we're just solving for different things depending on what's given in the question. All right, so that summarizes chapter 5. So this is where midterm 2 material will end.